So let's take a look at how we would graph an exponential function. First of all, please notice that the form y equals c times a to the x power still holds. But in this problem right here, the c is hidden. In other words, this is 1 times 2 to the x power. So our initial value in this is 1. And we can prove that because if we plug in 0, initial value of x equals 0, we're going to get 2 to the 0 power, which is 1. 2 to the 0 power, which is 1. And so our initial value is 1. That makes this, the 2, becomes our growth factor. So I am going to be multiplying each step by 2 times the 1 in front of it. It's our doubling problem again. So 1 times 2 is 2. 2 times 2 is 4. 4 times 2 is 8. So if I wanted to plot these points, I would start with 0, 1. My initial value, 0, 1. Sorry, that one's not actually there. 0, 1. Then 1, 2. So right 1, up 2. And then 2, 4. Right 2, up 4. Right 3, up 8. Okay? Can you see the curve that's happening? Can you see the growth that is taking place in my graph, which is smooth and continuous? Well, let's take a look at what happens on the negative exponent side. The negative exponent, remember, 2 to the negative 1 is the same thing as 1/2 to the positive 1. That's going to make this 1/2. And 1/2 times 2 is equal to 1. How can I find the number before it, though? I'm not going to multiply by 2. But what if in my head I divided by 2, making this 1/4, and then recognize that 1/4 times 2 is 1/2. Divide by 2 makes this 1/8, and 1/8 times 2 is 1/4. So in this part, we're actually in our head, we're sort of working backwards. We're dividing everything by 2 just to find those negative values. We're doing the inverse operation. We're dividing 1 divided by 2, 1/2 divided by 2, 1/4 divided by 2. Now, it really still is times 2 for our growth factor when you start at the lowest value to the highest, but to find those, we kind of worked backwards in a concept. So let's graph those points. -1, 1/2, -2, 1/4, -3, 1/8. Now notice it's curving in again. Can I ever get a negative number? Is there ever going to be a time with this initial problem that I can have a negative number? Or is this denominator just going to keep getting bigger and bigger and bigger, meaning that the fraction is getting closer and closer without ever reaching 0? That is called an asymptote. Remember that from earlier in the year? That's called a horizontal asymptote. And that's y equals 0 is the horizontal asymptote of our problem. So an exponential growth is going to be always increasing. It's going to rise from the left. As x gets bigger, the graph will get bigger. The a value is a positive number, which is greater than 1. The horizontal asymptote is at y equals 0. The domain is all real numbers. I can plug in anything I want. But the range, no matter what I type in, will always be a number that is greater than 0. So let's take a look at our summary here. It says, hey, anytime a is greater than 1, anytime my growth value is greater than 1, I have a growth function. Now there's some rules. It's all real numbers for the domain. The range is positive real numbers. It will never cross the x-axis. The y-intercept will be 1 unless my c value is something different. Notice there's no different c value in this problem. So this is like the parent exponential function. The x-axis, or y equals 0, is the horizontal asymptote. The function a to the x, a will always have to be positive. It will always be increasing. It's a 1-to-1 function. Now this next one's it's nice to have, but it's not necessarily, you don't need to memorize it. that this point will always exist. Unless that initial value is something different, it will always cross through 0, 1. And it will always cross through 1, whatever A growth factor is. So 1, 2 in this case. See how it crossed through the point 1, 2. And it will cross through negative 1, 1 over that growth factor. So negative 1, 1 over 2. Like I said, I wouldn't necessarily memorize this, but it is nice to know. The graph has to be smooth and continuous with no corners or gaps. Well, what if the growth factor isn't bigger than 1? What if the growth factor here happens to be between 0 and 1? Still has to be positive. We've already said that A must always be a positive value, but it's smaller than 1. In other words, it's a proper fraction. Well, what's my initial value? My initial value is still 1. If I made this to the first power, 1/2 to the first power is 1/2. 1/2 to the second power is equal to 1 over 2 squared, so that's 1/4. And hopefully you'll notice over here what we're doing is we are multiplying each time times 1/2 times 1/2, which is going to make this 1/8. And again, the denominator is getting larger and larger and larger, which means my y values are getting closer and closer to 0, but they're never actually going to cross the x-axis. They're never going to equal 0. And if I needed the negative values, I could work backwards. Instead of multiplying by 1/2, I could divide by 1/2, which is the same thing as times 2, times 2, times 2. Now, if you look going forward, that's still times 1/2. That's still times 1/2, and that's still times 1/2, so that my growth factor is 1/2. But it's actually called now decay, because if you'll notice, my values are actually decreasing as x gets larger. The values are decreasing as x gets larger. The domain is still all real numbers. The range is still greater than 0. Sorry, the range is greater than 0. And the horizontal asymptote is still y equals 0, or the x-axis. Let's put that into some summary. And here's our summary box. Notice that here we have A is between 0 and 1. We do not have an initial value other than 1. Our initial value is actually 1 here. It is all real numbers. The range is a set of positive real numbers. There is no x-intercept. The y-intercept is at 1, meaning that it passes through 0, 1. This time, notice it went through 1 and then 1 over A, okay? Or actually, it's still 1A, but A is 1/2 in this case. And this is negative 1, 1 over 1/2, which made that value 2. It is smooth and continuous with no corners and no gaps. It is a decreasing function. Well, if we have functions, so in other words, I had a growth function here, 2 to the x power. I had a decay function here, 1/2 to the x power. I can also transform that function. I can take that function and do things to it. If I took 2, instead of 2 to the x, which is my original parent function, and I made it 2 to the negative x, isn't that the same thing as 1/2 to the x? 2 to the negative x is 1/2 to the x. And so what was 1/2 to the x power? This was 1/2 to the x power. How do those two graphs relate to each other? Look at how this one is set up with the x and y axis. And now look at this graph. Aren't they reflections of each other across the y-axis? In other words, that is a horizontal reflection. And if you look at the problem here, do you see that that negative sign is up there with the exponent, that negative x right there? It's telling me reflected over the y-axis, which is what we effectively did here. And then it's telling me to move that function down 3. So I'm going to start with, I'm not going to start with 2 to the x, I'm actually going to start with 1/2 to the x. And I'm going to plug in the values that I've already found for this function. We found 8, 4, 2, 1, 1/2, 1/4, and 1/8. Okay, and we plot those points. We've got 0, 1, we've got 1, 1, 1/2, that one's not there, 1/4, 1/8, but -1, 2, -2, 4, and -3, 8. So here is 1/2 to the x power. Now, if I'm going to take that function, 1/2 to the x, and I'm going to move it down 3, what's affected? Well, it's not the x values that are affected. The x values are still going to stay the same. They have not changed. But the y values are going to drop 3. In other words, I'm going to take each y value and I'm going to move it down 3 spaces. 1/2 minus 3 is -2.5. 1/4 minus 3 is -2 3/4. 1/8 minus 3 is -2 7/8. What am I approaching in this case? What am I getting closer and closer to? Well, let's plot those points and look. I've got -3, 5. Let me use a different color. -3, 5. -2, 1. -1, -1. 0, -2, and then 1, -2.5, -2 3/4, -2 7/8. We're approaching that line right there. We are approaching the -3. This is approaching -3. My horizontal asymptote is now y equals -3, because as the graph moved down 3, so did the horizontal asymptote. And although the domain is still all real numbers, the range is now shifted down 3 also. The range isn't greater than 0 anymore because these numbers down here are below 0. The range is greater than -3. So the vertical shift told me what to do with the range, and the vertical shift told me what to do with the horizontal asymptote.